In previous videos, we've taken a look at the magazine, the tool length measuring sensor, the part height sensor, and we looked at the mechanical capabilities of the actuator that loosens and tightens the collet. In this video, we're going to take a look at the electronics that drive the actuator, as well as the microcontroller that helps provide an interface between the Centroid Acorn controller and the stepper driver that's used for this particular motor. It's quite an interesting combination of components to yield the results that were desired. As I've mentioned in previous videos, I'm using the Centroid Acorn controller for this CNC machine. Very good controller, handles everything I needed it to do, except that I couldn't communicate out of it via a serial interface. And that was very important for what I'm trying to do with this actuator, because I needed to set the current level for the output of the stepper driver, and that is performed via serial. We'll take a look at that in a bit more detail once we discuss the stepper driver. So in order to do that, I had to utilize something in between the Centroid Acorn controller and that stepper driver. For that function, I decided to go with the Raspberry Pi PICO controller. It's a $4 microcontroller board. Very nice, very affordable, works very much like an Arduino or any of those type of products, but cheaper for the most part. And it's by the Raspberry Pi organization, and I like their other components and products as well, so I thought I'd give it a try, and frankly it worked beautifully. So let's take a quick look at this particular board and its related components. The purpose of the PICO is to take 4 discrete outputs coming from the relays of the Acorn and turn those into translated serial commands to set the current level, which in turn sets the torque level of the stepper driver for the actuator. So we've got 4 outputs coming from Acorn. We'll just simply call it low current, medium high current, and high current. And that would translate into low torque, medium high torque, and high torque for that actuator. That allows us to control very precisely how much force I put into that collet nut as I'm rotating the socket. The rest of the components here on this board are a voltage translator, a logic level translator between the PICO logic at 3.3 volts and the stepper driver logic level, which is 5 volts. So that's all that device is in the middle, and then the bar graph on the far right is just an indicator for easy reference, mostly when I was debugging it, so that I'd know that the PICO was saying I'm getting set for low torque, which would be the blue light, normal torque or mid torque, which would be green, medium high torque yellow, and then the far right LED is red for ultra high or the highest level of torque control. The stepper driver I'm using for the actuator is from Pololu. It's the model TIC 825, and it provides, I believe, 3.5 amps of power. And it's programmable in that via serial command I can set the output current going to the motor, which then in turn allows me to set the torque amount for that motor. Very ingenious system. Unfortunately, as mentioned earlier, the Acorn didn't allow me to communicate with it via serial, but I do use the Acorn to provide it step and direction signals via the A-axis interface of the Acorn control. So it's just like another axis on the machine. I program it with angles that I want it to move to. Very, very nice system. But all around, this was the magic piece to the whole puzzle for making this automatic tool changing system work. Without it, I wouldn't have been able to set the torque control to adjust how tight or how loose, I keep that collet nut after tightening the tool. Remember, if I were to go to full tightness, 100% power on that motor and tighten up the collet nut, when I go to loosen the collet nut, I may not have enough power to loosen it. So what I do is I set the current at about 80% for tightening, and that's been more than adequate for the tools that I'm using. Then when I go to loosen the collet nut, I run it at 100% current to break the collet nut free, and then I'll reduce the current back down to a more usable current level. And that way I don't have to add auxiliary cooling or anything to this stepper driver. Frankly, it just runs passive as it is because I'm using it very infrequently and only for a few seconds at a time. Now we'll take a quick look at the MicroPython program that's running in the PICO that handles this translation between Acorn output and the serial input to the stepper driver. I'm not going to go into great detail here, otherwise it'll take way too long, but we're just going to import a few libraries. We're going to set up some outputs that are used to turn on the LEDs on the bar graph. We're going to set up some inputs to take inputs from the Acorn for the various current settings that we want. We'll set up our COM port for communication with the stepper drive. We're going to have a few functions here that are needed to work with that stepper drive, basically setting it in a couple of different modes. And then this function is what actually communicates to the stepper drive what particular current level that we want. This function simply handles the bar graph to indicate what current level by illuminating one of the LEDs on it. In here, we're going to do some initial housekeeping to make sure everything's communicating fine between the PICO and the stepper driver. And then we go into our main loop, which simply looks for our inputs and compares the last current of the PICO to determine if it was an idle mode, low mode, tighten mode, or loosen mode. And based on an input, if it's different from that, then obviously the state is changed, and we'll set the current value into the stepper driver and then update the bar graph to show us what it's actually doing. And then finally, like I like to do with a lot of programs like this, where you don't have a user interface, I just throw a LED flasher on there that beats about every couple of seconds or something like that, and I call it a heartbeat. And then if the program exits for whatever reason, in debugging it would print program terminated. So realistically, the program is very, very small and concise that's inside the PICO to handle that translation between the Acorn and the stepper driver. Now let's go through and do a step-by-step breakdown of all the different operations and how it relates in the macro code. First we'll go through, watch the video of the tightening sequence, and then we'll go through it again the second time, stopping it at various points so I can point out what's going on in the macro program. Okay, at the beginning of the program, or the macro, we're going to set up some user variables, do our logic skip when we're graphing and searching and so forth. And then we're going to go through and do some preparatory moves to position the spindle over the top of the socket. We'll set our current we'll set the outputs with these M codes to set the current that goes through, as you remember, goes through the PICO and then gets communicated over to the stepper driver. We'll set that torque level. And in this case, I want it set to the tightening level, which is approximately 90% on that tick drive. Now, we're not going to see the socket engagement loop perform its actions because the socket is already aligned and therefore it just enters the socket. For the wrench engagement loop, we only really saw it advance the wrench. It was already aligned, or the flats on the spindle were already aligned with the flats of the wrench, so it tested OK right away and moved on to the next step. We'll look at that in more detail in the loosening sequence. This section of the code really handles a lot of stuff all at the same time in this little loop. What we're going to do is start out by setting our tightening angle to an increment of 50 degrees, meaning we're going to rotate 50 degrees for each tightening test. And then if we didn't verify that the collet nut is tight, we'll repeat that 50 degrees of rotation until that nut is finally tight. We're going to do a little bit of cleanup on the variables here and there, set some starting values, and then we're going to start rotating the socket. And that's this G01, G91, feed incremental A, the 50 degrees at a feed rate that is predefined by variable F, # number 108. We're going to monitor the encoder position because that's what we're going to use to actually determine if, in fact, the collet nut is tight. So we're going to monitor its ending value at the end of the motion, and then we're going to do a comparison between its starting and ending value, and then we will compare that against how far it should have rotated. If as we get down here, where is that? Right here. If that amount of rotation, if the actual rotation was less than 75% of what it should be, that tells me that the stepper motor stalled out, and therefore I can assume that the collet nut is tight. But if it is more than 75%, it might be right on the edge of being tight and not tight, so I'm going to give it one more shot to really tighten up that collet nut. And, you know, again, the stepper motor's just stalled out, and that's what's making that chattering sound, and that's perfectly fine. It's not going to hurt the stepper motor or the gearbox or the spindle. It's actually a very low force, but kind of helps tighten the nut a little bit, and it kind of sounds like an impact driver, but it's certainly not functioning in that regard. Now with the collet nut tight, we're just simply going to retract the wrench. We will, of course, send the command to unlock the spindle, which retracts the wrench. We will verify that it has retracted. In this case, it did retract on the first try, but we verify that before moving on to the next step. Because the next thing is to retract Z-axis up to home position. If that wrench is still in position, we just broke the actuator. So anyhow, we retract the wrench, home the machine, switch back to the original coordinate system, and reset the torque setting at the stepper driver to its lowest level so that it doesn't generate a lot of heat or, basically waste energy. And that wraps up this macro for the tightening sequence. Now let's move on to the loosening sequence. Some of the exact same steps are performed, so we'll cover those that weren't covered in the previous section where we were tightening the collet. As with the previous macro, we're going to start out by establishing some user variables, handle our bypass for graphing and searching and so forth, and then we'll make the preparatory move to get the spindle over the top of the socket, and then bring Z down so it's above the socket but not yet engaged, and set our torque to a low level for positioning. Now we enter into the socket engagement loop, and the purpose of this loop is, of course, to align the flats of the collet nut with the flats in the socket. There's no guarantee that those will ever be in a line, so we've always got to test it first and then make an adjustment with the rotation of the socket to align with the collet nut, and then try again. And we keep repeating that process until we can move down to full depth in Z, full engagement depth in Z, and then if the switch that monitors the position of the socket being either up or down, if it is in fact still up and the spindle is down at depth, we know we've accomplished the mission. If not, it'll just keep going around and around at a 5-degree increment and keep trying until it finally succeeds. The wrench engagement loop, as mentioned in the tightening sequence, is the same. We're going to advance the wrench if the switch, in this case I'm looking at this system variable 50044, if that is showing that the spindle is engaged, we're good to go and move on. If not, I'm going to rotate the A-axis about 2 degrees, or precisely 2 degrees, and then repeat the test again and keep repeating this until the wrench can finally move forward, fully engaging with the flats on the spindle itself. In order to understand what this loop is doing, you will have had to have understood how to loosen an ER-style collet. When you go to loosen it with wrenches, you'll notice at first it's very tight. You'll unscrew the nut about 20-30 degrees or so, and then it'll seem like the nut becomes free and everything is loose. Well, that's not the true case. The collet itself is stuck in the taper of the spindle. So what you have to do is continue to unscrew the nut until the collet is drawn out of the taper lock with the spindle. And that totals about 480 degrees, give or take a little bit. So you'll see that happen in the video, and then you'll see the video, the spindle or the socket retightens the collet. Well, it's just bringing up into a slight tension there so that when we transport the tool back over to the magazine, there's a little tension on the collet so the tool can't fall out. So a quick look at the code, we'll see that we're going to set the current to the loosening level, which is maximum power. We'll set up a few variables, and then we're going to loosen the collet to 30 degrees at a very low feed rate. As you know, with stepper motors, the faster you spin them, the lower the torque they output. So by going with a low feed rate at maximum current and therefore maximum power, I've got the maximum amount of torque available to me to loosen that collet nut. At that point, at about 30 degrees, we've broke the collet loose. Now we're going to go to a total of 480 degrees. And that will draw the collet out of the taper of the spindle. It breaks that taper lock. We're going to verify that all the rotations actually occurred by looking at the encoder values and comparing them. If the encoder does show that the motor rotated through this entire process, we're in really good shape knowing that the tool is in fact loose and we can extract it from the spindle. The next step up after all of that is we're going to rotate back to a tightening sequence and retighten the collet, but we only bring it up to a slight tension so that the tool doesn't fall out of the collet. In truth, the way my collet is, tools don't fall out anyhow, but I like to get back to a good starting point, which is just slightly tighten on that collet nut. And as the case with the tightening sequence, we're going to retract the wrench that as before is done in a loop just to verify. We give it the command to unlock the spindle, check the switch to make sure the wrench is in fact retracted before moving on to finishing up the macro, which will take z-axis home, set things back to the way they were before the macro started so that the program can continue with its machining operations. Well, with that, I believe we've covered every aspect of the automatic tool changing system on this CNC router. I certainly hope that you were inspired to maybe try something on your own of equal capability and so forth, and not to fear reaching out or trying things that are a little bit outside your comfort zone. I know I started this project with the Mach software on this machine, found out I didn't really like that and switched over to the Centroid Acorn, and net result is I'm really pleased with the overall system. I will be putting out a few more videos on this CNC router in the future, and if you would like to be notified, please subscribe. It costs you nothing, it's free, and you don't even get spam emails or anything. You'll just get notifications that a new video has been released by Making Stuff with Chris DeHut, and I hope to see you again in future videos. Thanks again for watching. I'm Chris DeHut for Making Stuff with Chris DeHut. If you'd like to see other videos about this router or about CNC routing, please let me know in the comments below.